Okay, well, welcome everyone to our second to last Warren lecture of the semester. Thank you for coming. Today we're going to have Dr. Shiling Pei from the Colorado School of Mines come to talk to us about some really neat timber and tall wood projects. Dr. Pei, as I said, is a professor in the Department of Civil Environmental Engineering at the Colorado School of Mines. His research focuses on traditional and innovative timber systems. You can see one on the screen already, looking at performance-based design, numerical modeling, and dynamic behavior. He's done quite a bit of work in post-disaster reconnaissance as well, after different tornadoes and hurricanes, trying to understand the performance of timber structures. And he recently led an NSF-funded project collaborating with 6 different universities and all sorts of sponsors to build and test the structure you see in the photo here at the UCSD Shake Table. So join me in welcoming Dr. Pei.
Thanks, Ben. As I know, I did my homework, and you do have a wood design class in this campus. How many people are taking that course? Not as popular as concrete steel. So I asked Ben that what should I talk. I say, okay, I can talk about my project, but I think since this is not Pacific Northwest, it's not a timber country, so I divided my lecture into half of introduction on mass timber, this new trend, and then half on my research. So even if you don't know anything about timber, it's fine. We look at the challenges of the 21st century. We think about, as structural engineers, it's a fighting between urbanization, where we need more houses, and climate change, because whatever human activity we do nowadays seems like to have a negative impact for some reason. I don't know. But construction industry is actually specifically guilty of this, because if you look at we're congregating into cities, we need to provide more density in housing. We build our cities out of steel and concrete. In combined, they are responsible for about 8% of total carbon emissions for humankind, which actually surprisingly out. And there's other studies you see from some colleague of mine who study building energy and all that. The buildings, this is just like the first down payment, right? Then you have to maintain the building, use energy to cool down the building or heat it up. It's a lot of energy. But the things I studied on, or the need coming out of this building infrastructure development, is more focused on the down payment side, which is like what we use to build our buildings. The use of timber has been around for thousands of years. In fact, it's actually, I think, aside from mud and stone, it is the first engineered material human ever utilized to build our infrastructure. The material, different than steel and concrete, it is actually grown by the power of sun, and they actually suck CO2 out of atmosphere and materialize it into fiber, where it provides strength to build our material. As you can see, 1 cubic meter of wood, if you can take it and put it in a building, that building is going to be here for, you'll be surprised. You go, in some old neighborhood, you see like just stick-built buildings, they've been there for 100 years. It's going to be sequester that carbon for a long time. In fact, I'm coming from Colorado School of Mines. There's people actually actively grab CO2 and pump them down into the empty mine shaft to store them. But why don't we just build more wood buildings? The issue of wood buildings, if you look at, I mean, some of you took the class, it's what we call a light frame wood construction. That's the most common in modern history. In older times, like in Japan, Europe, you have what we call a heavy timber structure where they just use the whole tree, they cut it, and they build it. But the issue with these is that although there's some pretty cool structure, like in Japan, you have 5-story pagodas, but our cities doesn't look like that. We need something like this. You go above ground, and you look around, you see skyscrapers and tall buildings. Probably at the rate of urbanization right now, we don't need to be like China, where people all live in 30-story apartments. But I think hit something between 10-story and 20-story, that would be kind of ideal for a population density like the US and the Western world. So can we build wood that high? Because, yeah, this is a slide I steal from Michael Green, who did a TED Talk. The name of the TED Talk is Why Should We Build Wooden Skyscrapers? If you haven't heard or watched that TED Talk and you're interested, you should search it up. But the point I make is that back then when he did the slide in Canada, because he's a Canadian architect, the building code allow maximum height of a wood building in Canada at that time is 4 stories. Now we have great improvement. It's going to increase to 6. Okay. In the US, in light frame wood, it's typically 85 feet by IBC standard. But if you look at the natural trees, they can grow up to about 40 feet. In fact, the most common used wood species that we use to build our 4-story or 6-story building is a 33-story tall ones. We call them Douglas fir, or it's a fir family species. So strength-wise, you don't need to worry too much. The way we build it, in ancient time, if you want to build a big, tall building, you need a big, tall tree. It's like, yeah, this is a picture of me. This past summer, I was visiting Tokyo. They have the largest wooden torii door in Japan. Yeah, just look at that. It's pretty amazing. But yeah, we don't have that anymore. What we have commercially available nowadays is fast-growing, small-diameter lumber. But we also developed technology to actually, glue them together to whatever size we want. Glue lamp technology. A lot of people ask me about mass timber and others say, "Oh, how is the glue toxic?" Yeah, we've been using. Nothing is new, right? We've been using glued-up timber members for very, very long time. If you go just drive around the US, like in South Dakota, where I taught for 3 years, there's a wood bridges on the highway system for decades. But what really kickstarted the mass timber movement, as we see, is a system we call CLT, cross-laminated timber. The concept is quite simple. You just take a lot of small dimensional lumber. In fact, most of those, what we say laminus, they are smaller than your typical 2x4. In fact, they took 2x4, then they plane them to be even smaller. Then they cross-laminate them. Then you can have any even number of layers. Like you have 3-ply, 5 or 7 or 9-ply at some point. Then suddenly you have the ability to build the entire building, not just your columns and beams, but the entire building with the walls and diaphragm, everything with solid wood. Because before this, if you want the diaphragm, you have to do the joist, so use the OSB. They run into the same problem with why we don't build wood very tall in the first place because of fire. So the picture you see that before is one type of CLT building where we call it like honeycomb. Some people call it panelized construction, where you build everything out of panels. Advantage is that it's very stable, it's very easy, just like logo. The drawback is that you don't have a space like this. It's hard to do because the CLT panels, depending on how thick they are, they only span about 20, like 30 feet would be stretching it. But then you combine that with a beam column grid, and you can have a column, beam, you have purlin. So you can reduce that spacing, then you can do open space like this. So basically there's two types of main modern mass timber building nowadays. Then I talk about fire, right? So fire is kind of interesting because it is counterintuitive. Fire is actually the one of the perks for mass timber. If you think about doing something out of wood, in fact, under high temperature, the wood is the only construction material that can resist high temperature for prolonged duration. You say, well, what about steel? What about concrete? Concrete is nothing wrong with concrete, but it's mostly the steel. Because steel, when the temperature became so hot, like in an enclosed fire situation like this picture, it is from a 1904-06 San Francisco earthquake. After earthquake, there's fire. Then it's an enclosed warehouse situation. When you have enclosed fire, temperature rose to thousands of degrees. The steel under that high temperature start to soften a little bit. Once it softens, you see things like this. In the case of World Trade Center from the NIST report, it's not the initial impact, but the fire that softened the steel column. Then you have a lower E. Then your buckling load is calculated by the EI, then things buckle. But wood, on the other hand, they burn, yeah, of course. But once they burn, they form a char layer. In fact, in the wood fire design, we use a factor of about, I think, don't quote me on this, but like half an inch per hour of char layer. So once your char layer develop to like an inch or 2 inches, it's hard to burn it through. For example, like this is a picture of a building they tested in Canada. It's just chamber where they use the gas to burn it for like 3 hours. Inside it looks pretty bad, but the researcher can actually put his hand on the other side. So in fire design, if you actually contain the fire within wood, it can actually withstand a lot of fire. So you combine all that benefit of utilizing mass timber components, including large section glulamps and also mass timber panels. You have a new way to build tall buildings in almost 100 years. If you define tall building as any building that's above 10 stories, why is 10 stories? I'll tell you why later. So the first tall steel building is in Chicago. That was built in 1884. And then the first one in concrete is in Cincinnati, 1903. Then after that, if you want to build anything above 10 stories, you have to use those two types of materials until that record gets broken by 2012, which is more than 13 years ago in Australia. Forte building is 10 stories. Apparently that is 13 years ago. So what is it now? About 10 years later, you have the Norway building. That's 18 stories, all wood. This one's kind of interesting. In fact, last year they have the World Conference on Timber Engineering in Norway. Some people actually lived in, this is a hotel. They kind of stay there. I didn't get to go because I didn't get my visa. So, and then right now, the world record holder is actually not that far from here in Milwaukee. 25-story mass timber building, but it cheated a little bit because it is actually 8-story concrete plus 17-story mass timber. So this one, 18-story, is full wood. So yeah, you probably already heard about this term called mass timber movement. In fact, it's not just US, it's around the world, but specifically if you look at the United States. The project that involves mass timber, regardless of height, because most of them, sometimes they're like malls, you're 2-story and 3. There's about 2,000 projects around the US that's been planned or has already built. In fact, like 1,000 of them, so it's already built or under construction. There's a new trend for a sort of hybrid approach where they will use mass timber gravity system, like what I showed you, the glue lines, beams, and columns, and panels. The lateral system, they will use either a concrete core or a steel brace frame. Why? Because there's no code recognized lateral system made out of mass timber yet. There's one, but people, for some reason, they don't use it that much. And then you notice a lot of those projects are happening in seismic active region. So the idea of my research project, so now kind of pivoting to what I do, I don't do like all mass timber, just one aspect, is to think, if we're going to build that many mass timber buildings in that, and then instead of bringing a concrete contractor, a steel contractor, can we do everything in wood? And if we can do everything in wood, simplify and streamline the construction process, hopefully save money. And also, maybe if nobody ever done that, it's a new type of combination. It's actually not a combination, it's just mass timber gravity system plus the mass timber lateral system. Could we do it better? Could we do it right the first time to actually make our lateral systems more resilient than what's already been observed? Then I assume a lot of you, although there's no wood class, but everybody knows what the resiliency is, right? People talk about resiliency. But seismically, I think a picture is better than 1,000 words. We can look at a very classic example of how the modern code system or modern design philosophy gave us in face of a large earthquake in a highly populated region. In this case, New Zealand Christchurch earthquake. It's a magnitude 6 earthquake. This picture is taken like 3 minutes after the main shake from a kind of weather camera from a mountain nearby where the entire downtown's in dust. What's more interesting is that after about 3 years, you look at the street view of Christchurch before and after, and then you just kind of walk around the city and see those things again and again. What you see is, for some reason, after earthquake, people prefer parking lots instead of buildings. This is what they call rebuild. So you got a system that you got an event, right? It's not so much of a disaster from a coyote standpoint. Of course, even one coyote is not good. But in fact, most of the coyote, like 180 some, came from like one collapsed building in Christchurch, if you do the research. So most of the buildings, they did very good. They did exactly what our design code asked them to do, is that they sacrifice themselves to dissipate energy, but remain standing so people can get out. But the building, they die. So this is called the code compliant or life safety requirement, which is the philosophy followed by most of the developed countries, with the exception of probably Japan, maybe Chile. So if something like that happens in like downtown LA again, like Northridge, we'll have the same thing. What we really want is this. This is called resilience performance. So we don't want a building to sacrifice themselves, which means during an earthquake, we want building to not only withstand, but also be at least repairable after earthquake. And wood is really in a good position to do that. Even 16 years ago, not that far, 16 years ago, 2009, back then, there's already mass timber in Europe, but we don't know that yet. Like myself, as a postdoc back then, and my advisor, Professor John Vanderlyn, we went to Japan and we tested a full-scale apartment building built with light frame wood construction We selected to be 6-story tall because that's the, like I said, tallest at that point we can build. So we tested this under a Northridge earthquake times 1.8. So that's a test you're going to see here. It's a 3D test, and you see the room here on the corner where it has the lights on. The like little plates you see there, those are the added mass. You know, you got to do the math right. So we went to Japan and we built this building. We built it in about 4 months, and then we ran 5 tests. So typically, when you do a big test, you do small design level, and then this, which we'll call MCE. And then after that, we check the building. I believe it's actually not on the 1st story. It's on the 3rd or 2nd story. You see most of the damage, the drywall crack, some nail pull out. But building is great. It's actually repairable. Then after that, there's some other researchers around the world. They start to say, okay, well, could we do the same thing with mass timber? So this is a friend of mine who's Professor Isoda at Kyoto University. They did a test of a 5-story CLT building, also at E-Defense. Those tests basically give us confidence because wood is very flexible and lightweight, about a quarter of the unit weight of concrete. So yeah, we can do that, but the difficult of those problem is that traditional wood construction, including mass timber, the ductility develops within the connections. If you want to develop ductility in connections for concrete, you need to yield your rebar. For wood, you need to have some sort of damage, the pull out of nails or things like that. So can we go beyond that? The idea came from actually New Zealand at the University of Canterbury, where there are a bunch of researchers. They started as they're PT guys, they're PT concrete guys, PT concrete frame and all that. Then suddenly, because New Zealand, they also just like Canada, they export a lot of timber. They're like, could we do PT on timber? So they start to think about, okay, we can do what we call a rocking wall, which is, again, not a new concept. Precast concrete rocking walls being in existence. But the idea, if you never heard of it, is just like a push puppet, where you have a PT bar on a block of wood or concrete. Then when earthquake comes, it'll rock. And then if you fine-tune the PT force and concrete, the PT force geometry of your block, and also the area of the reinforcement to be not yielding during that period, then after earthquake, you're going to self-center. So we want to use that to replace construction, like I mentioned, a hybrid construction like this. Use the concrete tower with, no, we don't want concrete tower. We want everything wood, using rocking wall. So that brings us to fast forward a couple of years, the NHERI TallWood project, where we, in fact, we didn't go directly to a 10-story test. We actually did our normal component level. We test some walls at WSU around 2015. Then we did a 2-story test on the UCSC shake table at 2017. Then we get to the 10-story, where it's the same picture you see on the title slides. And this is the tallest full-scale building ever tested on a shake table around the world. I think we're going to have that record for a while. The UCSC shake table, for some of you don't know, it's apparently in San Diego, and it's outdoor, which means you can build as high as you want. But of course, you need to pay attention to your aspect ratio, because you don't want to test the pencil. That's not representative. It turns out, what we find out is like a 10-story is almost like the limit of that aspect ratio could still kind of happen in real life. It almost represents a worst case scenario. So that's why we choose 10. And another kind of funny thing is that I always jokingly saying that the only contribution I have to the NHERI TallWood project is to decide that it has to be 10-story. Because first, it's double digits. Secondly, it's easier to fundraise. So when we proposed the project, the UCSD shake table was only 1D. But during that time, they upgraded. And it suddenly becomes a 6-degree freedom shake table. Of course, we didn't do the rotational degree freedom in our test because seldom people does that. But this is actually very, very neat because I'm actually very happy about it because you spend so much effort and time to build up the building. You want to test in the what they call real earthquake in 3D. The test building itself, as you can see, the yellow outline is the shake table. So we placed all our gravity system. You see those columns. There's like 12 of them. Oh, actually, yeah. Yes, there are 12 of them, or actually 14 of them. And then we use overhand to point out so that we can have some patio where we can have a different building facade to look at non-structural performance because we want to reach resiliency, which we want to also minimize damage to non-structural systems. The building itself is it's like a mass timber products museum because we get donations from everywhere. There are 2 rocking wall pairs. One of them are built with what we call mass plywood panel. It's just plywood, but then you just keep doing it until it's like this thick. Then you have CLT on the other direction. Then we have CLT and what we call GLT from Europe, which is donated for those 4 stories. And then we have nail laminated timber for the next 3-story, 4-story, 2-story. And then finally, another kind of a mass plywood type of product from Boise Cascade for the top 4-story. Then all the connections were donated by Simpson, except the ones that we have to specially design. The construction itself, it's actually quite fast. Remember, I talked about when we built a 6-story building in Japan, it took us 4 months. This one also took us, you look at it, you're like, oh, 5 months. But yeah, there's actually some little accident in the construction process. So we have to wait for a part to be manufactured. That slow us down. So really, you look at about 3 months to do the whole thing. Just to give you an idea of the scale, this is the last panel on the roof we put in. It's a drone shot. It's San Diego. So it's kind of beautiful. But on this side, you have the like rural San Diego. But when the camera pans, you see the downtown San Diego. The ocean's on this side. It is really, quite impressive. You see the red towers? Those are 6 stories tall. And they are there to prevent the specimen from collapsing into the white building down here, which is a control building with all the hydraulics. They're like, oh, yeah, we have a 6-story tall tower, should be enough. But, yeah. So the PI of the site actually asked me to bought some like anchor with steel cables to tie the top 4-story to the other side of the testing site. But in the end, everything works out. We didn't collapse it. I don't think they'll ever let us. So after the construction, we went into the what we call instrumentation phase. This is just a cool thing that we want to show. There's a collaborator at UCSD. They use LiDAR on the drone and handheld device. They walk the entire building. Then they merged all the point cloud into a single model where it's kind of neat. So if now I was not sure if this type of connector was used, I can actually go in and check every single screw in the point cloud database. Nobody ever done that, but the data is there. So the building is not there anymore, but yeah, this is very just pretty cool things that you use. The test program, apparently you're gonna kind of ramp it up. So we actually targeted at 5 levels. The building itself was designed for a location in Seattle. That location is actually chosen by the graduate student working on it. It's her favorite coffee shop in Seattle. So you can see we're trying to match the ASC7 response spectrum, multi-point response spectrum of the location. For the vertical, now that's kind of new for ASC7. We didn't try to match it, but it's kind of a ballpark. It's about right. But then the question is like, okay, how many earthquakes do we want to run? I was first asked about this, then I said I don't know. Because if you think about it, in Japan we run 5 tests. Then we have to stop because everything's cracking. Then on the 2-story test, I didn't show you, but 2-story mass timber with rocking wall, we ran 14 tests. So for this one, I say, oh yeah, we'll at least run 20. But, who knows, right? You just keep running, but it just refuses to get damaged. And then we're like, yeah, since we can get more data, why not? It's so much effort. So what we did is that we run a total of 88 tests on the first phase, where you can see the PGA, peak ground acceleration of the earthquakes. You can see we kind of ramp it up to design basis earthquake. Then we have a media day where we have the reporters and everything, NSF folks. And then after that, we get everybody out. Then we keep ranking it up to MCE, and then finish it off. So it's yeah. As a matter of fact, if we're not confined by the subsequent phases that coming after us, that we have to kind of get going, we could easily run more. I'll show you just, apparently not 88, but I'll show you one, but apparently it's going to be the largest one. This is the 75th test. Remember, this building has been going through 74 earthquakes, and about half of them are at the or above design level. And this is 75th without any repair or any care. So you see a top view that's from a drone, and then you see a close-up on one of the rocking walls at the base, and then the overall building. And also this is a 3D test, so you hear the vertical thing coming out first. You can very distinctly see the 2 phases of the dynamic response. The first phase is when earthquake input is have a lot of higher frequency component where you excite the building in a higher mode. And later when the earthquakes start to die down, you see the building revert to first mode, and the first mode actually produces the maximum displacement demand. The higher modes produce the maximum force demand. So the video you just see is kind of, we have to zoom out so far, but if you're actually in the building, as you can see the non-structural components, this is the facade where we use a sliding detail. You know exactly what I mean after you see how it moves. And then we have a GoPro camera look at the corner of those 2 facades from above. That's the first mode. Yeah, you move a lot. Yeah, this video is great because it actually proved 2 points. The first point is that if you detail your non-structural system carefully, they can remain damage-free. We didn't even break a single window. The second point is that non-structural systems, they don't have a ability to pull themselves back. But the fact that you see where they started exactly as where they ended, that means the building self-centered. So I don't even need to show you why it's self-centered. Because of non-structural system, they came back. You know the building is self-centered. Of course, we have other direct measurement evidence that there's no residual drift. Then this is some more non-structural detail. Yeah, we have that thing again. But you can see the stairs where we have the flexible joint on the stairs. And on the here, the drywall, we have the sliding detail on the top. You can see the top. And this is also one of the shake table, one of the earthquake record from Japan, from the Tahuko earthquake, the one with the big tsunami, you remember? That keeps shaking Tokyo for like 3 minutes. What you see here is 1 minute of strong motion. Yeah, it just goes on forever. And this one, the earthquake is so large that the shake table can only run it in 1D. So that's why you can only see it in 1D. But still, you see the exact same behavior, everything back to its initial position, and the building recentered. So after this, like I said, it's phase 1, 8A test. Then we had a researcher from Michigan Tech came in, and then he added 2 like huge dampers on one pair of the rocking walls. He did another 19 tests. Then we have our Japanese collaborator came in, and they removed our PT on the wall. Then they shipped some bigger PT from Japan, placed them in a different location on the wall using their design requirements, which is much stiffer than the US. They also replaced the energy dissipation device. They did another 51 test. And then we take the top 4-story off. They became a 6-story building, handed to Oregon State University researchers. They did another 3 phases and a total of 86 tests. So if you look at the just the gravity system of the bottom 6 stories, that's 244 earthquakes. It is likely the world's most shaken full-scale building. But out of all that, there's no structural damage and no residual drift. Of course, we have some drywall damage, as you can see, but stair, everything's fine. So what is the main takeaway? I say you still remember the resiliency target I showed you after the Christchurch earthquake. 0 building casualty, 0 people casualty. It's totally achievable and practical with mass timber construction. In fact, you don't even need to do too much. You just need to replace your concrete or steel core with post-tension mass timber rocking wall. Non-structural system, they go by the ride. And the gravity system is the key because you have to have a beam column joint that can go back and forth 1,000 times without losing strength. But it can be done, It's and we have a paper which is free for review. Just search my name and 10-story test, you get it. So what I'm working on now is try to put the mass timber rocking wall into the US code. We're trying to catch the ASC 7 updates in 2028. We're doing a P695 study supported by the Pankau Foundation with a very brilliant engineer, Ray Zimmerman from KPFF. So we'll see how it happens. We'll see how it works. The main takeaway, again, if you think of that, this is the tallest modern wood building that survived so many earthquakes. There's really nothing new under the sun, right? Japanese have been doing that for hundreds of years, even without a lateral system. If you ever visit Japan to see those temples, they don't have a lateral system. So, yeah, they must know something. So in the end, if you want to know more about the project or any other master project I'm doing, the best way is to just follow me on Twitter or X. In fact, I started my X account when we start building this. So if you just go look at my account and then scroll all the way down, you'll see step by step how this thing is built. A lot of companies and collaborators involved in this project. Of course, special thanks to National Science Foundation, because without the shared use facility, I mean, I'm coming from Colorado School of Mines. We don't have a lab, you know. It's like, I have a little shake table, but I never use it. And then finally, if you're interested in timber construction, I have a website. It's called timberengineering.org, where the idea is, I mean, it's not like a Facebook site, you know. It's a site where you can ask any question about timber engineering. I'll try to find some expert to reply to your post. Because nowadays, the social media became so self-centered. It's like, I got a site, it's about me. No, I mean, this one is about the question you have. It became a traditional forum type of thread. It's pretty cool. And then, yeah, if you go there, you can also find additional test footage, because I have a YouTube also. Yeah, nowadays, huh? All right, so that's all. Thank you very much. I'll be ready to take some questions.
So, who has questions?
Hey.
Thanks a lot, Ling. Always great to listen to this presentation. I have a question, a non-structural question about the non-structural components. So the facade, when you allow them to move with respect to one another,
Right.
it seems like they have an opening, and correct me if I'm wrong, if they don't. But if they do, how does that affect the energy efficiency of the building? Thank you again.
Yeah, the opening we saw is mostly on the corner. The short answer is I don't know, because my co-PI, Carrie Ryan, at Reno, she's kind of in charge of that. But I think, yeah, it will have some negative impact. I'm not an expert in building envelope. Yeah, it will not be as airtight as a traditional detail. But I think the trade-off is that if you're in Minnesota, I say go with the traditional. But if you're in San Francisco, maybe you can do the calculation, right? Say, you know, over 20 years, the energy I lost, is that worth it to implement that to let it survive an earthquake, or I can afford to just do traditional and just let it break? I think by the end of the day, it probably became a financial question, which will run some study. And then also, aside from that, the corner, we have some windows. Yeah, there are some companies, they actually do a elective suction test before and after. I don't think they published the result yet, but I think the results will be coming. Or maybe it's company, they'll make it proprietary, results are not good. But yeah, I think that's definitely a concern.
When do you decide when the building is not repairable? Is it like when the wood starts to splinter, or is it at some point before that?
Yeah, a building is repairable or not is always depending on how much money you want to pay. But for our case, you know, we actually send the student teams, each one focused on one area of the building. After every test, we go do inspection, try to find visible damage. And we also keep an eye on the natural period of the building. For this one, we didn't there's no visible detectable damage. We do see the natural period soften a little bit, but not to a point we're concerned that we need any repair or any special intervention. But for a typical wood building, like when I show the damage in like the Japanese test and some of the early tests on night frame, yeah, you see them. And then maybe it's more of a question of you ask your contractor, so is this repairable? Sometimes, like even for a CLT panel, when they're split and all that, you could essentially just cut that part out and then use epoxy to glue a new piece on. It's still repairable. But I think the main contribution of this one that I say, you don't need to repair is the self-centering aspect. Because for a building, after an earthquake, when it is slanted, permanently you have residual drift. That's when you say, maybe not. But as long as you don't have residual drift, I think most of the damage can be repairable as long as you feel it is economically to pay for it. Yeah, so that's our mentality. It's by the end of the day, it's the owner's choice. But if you have a 3% residual drift, I don't think it's the owner's choice. You get rate tag, then you got to tear it down anyway.
Okay, sounds good. Thank you for the great talk. Very interesting project. My question is kind of follow up on the conversation you just had on the behavior of the lateral system. With the post-tension elements, I'm assuming the goal is to keep them elastic because you want that recentering.
Yeah.
Okay, so with that, what would be the sacrificial element in your lateral system?
Oh, yeah. The sacrificial element is the, I didn't include this, but I included in our other talks when I have a little bit more time. It's the U-shaped flexural plate, which is not something, let me see if I can find the picture. It's not something new. Oh, yeah, here. Like those guys. It's a simple passive system which used extensively in concrete rocking walls. So we use the same thing. Yeah, that's a good question because for rocking wall, everything is elastic. So you got to dissipate energy at some time. And in fact, in our design methodology for this rocking wall system, we require the yieldable elements, which is the plastic element, to contribute at least, I think, 1/8 of the moment capacity. So that's how we ensure there's energy dissipation.
Did you implement them in all levels or certain levels that you thought are going to have drifts maximum?
Because the rocking wall system is balloon framed, it doesn't matter which level you put them in. So like in this case, we just distribute them evenly along the height. I think that's typically what people would do. But in some other cases, like there's a 6-story test phase I didn't show from Barbara Simpson from Stanford. She just concentrated them as two BRBs, two huge BRBs at the base. Either way, it's a rocking mechanism. So.
Okay. Thank you very much.
Yep.
Thank you very much. I have 2 questions. The first one is, how much of your gravity system uses steel connections? So it looks like your lateral system, you have some mix of steel and wood. I was curious for fire, how much of your gravity system includes any sort of steel connections?
It's all steel. I mean, we don't have any traditional carpentry. It's all steel hangers. But the fire situation is that for mass timber design, you bury your hangers beyond the char depths. So it is done that way. In fact, if you look at the reports online and all that, so if you want to see it, if you look at the design of the beams and columns, they're all over designed. They're designed for actually a 2-hour fire. And then if you just check structurally, they are like so over designed that you don't need that because the span's not that high. But our collaborator from Simpson Strong Tie, they want to make sure that we're mimicking the correct geometry of the joint. So that part, like a beam column, it's steel hanger. It's a special steel hanger that it's almost like a true pin. Then the column to column, we kind of use just rigid splice from Simpson Strong Tie. But at the very base of the gravity column, we use a 2D pin. They're all steel. Yeah, but there might be a way to do simpler connections than what we have implemented here. If you're building a real building, because the real building only see, one or two big earthquakes. And this one is a handful. So when we design, we actually, like a beam column joint, we actually design it so that it can withstand 5% drift without any damage. But that's a little bit overkill, but at least we got the methodology down. So what's your second one?
My second question was more on your structural identification throughout the test. So it looked like you had a series of small tests along the way. Were you using those for ID, or what was your objective there?
The ID is done by white noise. You know, for every test, every major test, before and after, we do white noise in 3 different directions. And later we found out that vertical doesn't do anything, so we did just 2. And then we actually, in my paper, if you read, there's a degradation of the stiffness, but we just can't see any damage. And also for non-linear system like this, the ID is using white noise. It's actually sometimes not that accurate because it doesn't engage the rocking mechanism. So the small earthquakes are really mostly to collect data. The IDs was done through white noise.
Sounds good. Well, I think we're over time now, so let's thank our speaker.
Thanks. Yeah.